Well, welcome back, wonderful physics students. We are going to walk through a rich example problem. So not a poor one, a rich one. Okay. So we are given this scenario. So we have a 10-kilogram block attached or pushed up against a spring, and this right here indicates this part from here all the way to B, there's no friction. You can tell friction starts because it gets like rough here. All right. So 10-kilogram block compresses the spring half a meter. So it's a large spring, and then is released. Oops, and this should be in you, but I caught all this. Okay, there we go. So we're given that the spring constant is 16,000 newtons per meter, and the spring is compressed half a meter, and we're given that the coefficient of friction of the rough patch is 0.2. Okay, so our first question is, how much energy is stored in the spring? So initially, all the energy is in the spring. Okay, so if you recall, well, why don't you try to do this? Pause the video and come back. Okay, so I hope you got it. Let's see, if you recall, the potential energy in a spring is equal to 1/2 k change in x, or change in s, squared. Okay, so this would be 1/2 times 16,000 times 0.5 squared. Okay, so since I don't have a calculator, we're going to talk this out. Half squared is a quarter. So 1/4 of 16,000 is 4,000, and half of 4,000 is 2,000. So this is 2,000. Now what are the units? That's right, joules. So we have 2,000 joules of energy stored in the spring, which means that our total energy is 2,000 joules. So now we release the block, and the block is traveling at some speed at A. And we want to know how much kinetic energy does the block have at point A. Well, let's see. It's no longer touching the spring. The block is no longer touching the spring. So all the energy that was in the spring bucket, so we still have 2,000 joules of energy, and the block didn't raise up, and it's not touching the spring anymore. So all the energy must be kinetic energy now. So we have 2,000 joules of kinetic energy. I could ask, what is the speed of the block at point A? Oops, I forgot. I missed a slide here. So this is new. And that was changing x. Okay, so what's the speed of the block at point A? Well, we know that the kinetic energy is equal to 2,000 joules, and that's equal to 1/2 mv squared. We know the mass is 10, so 1/2 of 10 is 5, so 2,000 divided by 5 is 400 equals v squared, and that just happens to equal 20 meters per second equals v. Pretty fast, 40 miles per hour. These are crazy numbers, but I'm able to do it in my head, so it works. Okay. So now, ooh, gosh, oh my god, this is supposed to be a change. This is a change, and this is mu. Okay. How far will the block slide past B before it comes to a stop? So now we're sliding past B over here. We want to find our change in x. So our kinetic energy is going to decrease. That means our total energy is going to decrease. We're doing werk. What? force is doing the work on the box? What force is outside our system taking energy away? Yes, that's right. It's friction. Friction is the culprit. It's taking the energy away. As the box slides along the rough surface, energy is lost due to heat and maybe making the box bump up a little bit, but it's a lot of thermal energy that's lost here, mainly thermal energy. So remember that werk is equal to F change in X. So let's draw a free body diagram of this box. And we have, as the box is moving, as the box is slowing down, we have the normal by the ground on the box, we have the weight by the earth on the box, and we have the friction by the ground on the box. Okay. So this friction is equal to mu n. Remember the fun equation. Mu is 0.2, and the normal in this case is equal to the weight, so that's about 100 newtons. So this is 20 newtons for the friction. Since friction is all parallel to change in x is going to the right, friction is going to the left. So the work is negative because we're losing energy. So we're losing 2,000 joules. We're not gaining it, we're losing it. And this is equal to 20 times our change in x. And you could say the 20 is backwards. That's where the negatives come. So 2,000 divided by 20 is 100 meters is equal to change in x. So that is how far the block slides. You could do this with just kinematics and forces if you wanted. You could say you could draw the free body diagram, solve for your acceleration, then use the kinematic equations to solve for your final velocity, or solve for your change in x. With this example, it's probably about equal amount of work both ways. Maybe this is a little bit quicker. This will become very handy to us in other more robust examples later on. Okay, well, that is our example. I hope this helps, and I look forward to working out some more examples with you in class.